Hello, it's Keith here, and this is lesson 10 of the platform-specific series of my 6809 assembly programming tutorials. Today we're going to be looking at the FM7 again, and we're going to be coming back to the Yamauchi commands. Now, if you didn't see my graphics tutorials, these are the commands that allow us to transfer a program as is to the sub-CPU, that's the CPU in charge of all graphics processing, and then run that command on the sub-CPU. And this is the only way we can get direct access to the VRAM on that system. Now, before we looked at the principle of how to do it, and I did a trick where I shifted one of the bit planes by a pixel just so we could see it happening. Now, what I actually wanted to do this time is take this a bit further and create something that would be viable in a real game. What I wanted to do is create a simple sprite drawing routine so we could see the potential speed that we could draw graphics in a real game and judge how good this system is in comparison to other systems, because often its games seem a little bit poor. Now, we did look at how to transfer sprites using the regular graphics commands, but this was relatively slow, and so this time we're looking at something approximating the best speed that this system can do now within the limitations of my abilities on the 6809, because I'm not very good at optimization on this system. But anyway, I think we're going to get a good example of how things look. Anyway, let's go over to our code and let's see the example in action. So here it is. Now this is going to use a set of 8x8 tiles. The example code we're looking at today draws an 8x8 sprite. Now the system works in bit planes, so there's 8 pixels per byte. So working in anything that's not a multiple of 8 wouldn't be very good. And I thought an 8x8 tile was a good sample. Now we're going to be using the tiles from the YQuest game I wrote before, but I have to point out, due to time constraints, I'm afraid I can't port that game to this system. But as an example, you know, this is very much viable for the kind of thing we would want to be doing. Now, it completely drew too fast there, so we didn't see it there. So I will just run this again, and we will hopefully see this running. Now, the code I've got here has the potential to draw 8 color tiles, or to skip one of the bit planes and draw 4 colors, which will be faster, and will leave some spare memory, which we'll discuss in a moment. Okay, so there we go. So that's how long it took to fill the entire screen. So that was 1 to 2 seconds or something of that kind of nature. Not amazingly fast, but not too bad, and certainly far better than we were looking at before. Now, the important thing to bear in mind is that it's the sub-CPU doing the draw commands. The main CPU was doing nothing. It was just waiting, basically. So even though that's not particularly fast, it doesn't mean that our game could be calculating what to draw in the next frame, and then we could create some kind of list of sprite draws for our sub CPU to do while the next sprite frame is being calculated. So it may not be as bad as it initially looks. Anyway, that's the best speed I've managed to achieve. That was 8 color tiles. We'll try it with 4 colors, which will be a third faster just because it's filling less data. There we go, that's not so bad. And that's using 4 colors, and we can remember redefine those 4 colors, and we will do that in a moment as well. Okay, well, let's just very quickly recap the tricks that we have to do to transfer data to the sub-CPU, in this case Yamauchi commands. We of course need to halt the sub-CPU, stopping the sub-CPU from functioning, transferring our data including the command to the shared area, and then enable it. Now the shared area is from FC80 onwards to FCFF, and this is at a different address on the sub-CPU. That's at D380. Now if we just go back to my other screen for a moment, we do have a list of the addresses here. So this is the main CPU RAM, and FC80 to FCFF is the shared area, and that data is the same effective area on the sub CPU, but it's a D380 to D3FF. Now you will see that there's various other areas here. This is ROM down here and IO, so we can't really use that. We've got a small area of work RAM here, not very much. This console buffer RAM is definitely available to us. We will be using that, but the vast majority of the other memory is actually being used by the screen. The red, blue and green bit planes. Now what we can actually do though is if we just use 2, in this case red and blue, which is why you saw those colors before, this would leave this area free, and the reason we might want that area is because we need somewhere to store our sprites, and if we've only got C000 to CFFF here, that's not very much memory, whereas if we don't use that bit plane, we can have all of this for our sprites, and that will give us something to draw onto the screen, and that's going to help us out. So we'll be looking at that as well. Anyway, these are the commands we're going to be using today to halt and release the CPU. I'm not going to go into the function of them. You can just take it from me, they work. We did cover them before, so please see the other graphics example if you want more details. And what we're going to do is we're going to transfer some data to the sub-CPU, so VRAM. We're going to transfer some tile bitmaps. These are our source data that we might want to copy to our screen. And we're going to transfer a program, not this one. This is a test version that's not working so well. This is our program that's going to copy a sprite from the unused areas of VRAM to the visible areas of VRAM. Let's actually have a look at it now, we might as well. So what it's going to do is it's going to copy from our source memory address U, which would be our sprite, to our destination memory address X, which would be somewhere on the screen, and we'd have to calculate that. Now the bit planes work down the screen, so each line of our sprite is 80 bytes below the first one, and that's because the screen is 80 bytes wide, so we're effectively moving down one line. And I've done this by adding them here, and I don't know if there's a faster way of doing this. I'm not so great at the 6809. This works. I did try this alternate version and it wasn't faster, so this is the best I've got so far. If you can think of something better, please let me know. Now this is doing the first 8 lines of the tile for the first bit plane. This is doing the second 8 lines, and the second bit plane starts hexadecimal 4000 afterwards. If you look at our memory map, you can see the first bit plane is here at quadruple 0, the second one's here at 4000, and the third one here, if we're using it, is at 8000. You can see that, and you can see that represented here. And if this definition is defined, we're using that third bit plane, and if it's not, we're not going to do it, which is why this would be faster. So that's our draw tile command, and that's our tile data. Now we need to transfer our tile data to somewhere in VRAM. By default, we're using C000 here as our VRAM for our sprites, and we've also got our tile routine, and we're storing that somewhere in VRAM, and we're using CF00 here. So that's the address we want to call to draw a single 8x8 tile in VRAM, and we need to make the sub-CPU call that, of course. Now we want to transfer these to VRAM, and so I've made a simple little function called transfer bytes. This will transfer 96 bytes each time we run it, and it will transfer them from a specified source, which is going to be X, and a specified destination, which is going to be D. Now you can see we store D into this command sequence here, and we're using a Yamauchi command to transfer the data for us. Now the reason we're only transferring 96 bytes each time is because the shared area is just 128 bytes, and we're using some of it for all this nonsense. So 96 is a good number to try and transfer each time. Now, one thing I do have to point out is last time I said the Yamauchi commands needed to have a special string Yamauchi after the 3F code byte. That's not entirely true. It was true on the FM8, but the FM7 and the FM77 do not check what the string contains. So rather than Yamauchi, I've put Llama-ichi this time, and that will work just fine. So it can be anything. There's not really such a small amount of space. We can't really store any spare data there, but it doesn't matter what's there. It doesn't check it. So there we're doing our move, and we're using self-modifying code here to store the new destination in here. The source is always going to be our shared area, and we're transferring the bytes to that shared area just here. So this is going to transfer 96 bytes fairly easily for us. Now we're going to need to transfer more than 96 bytes in some cases, but we can run the command multiple times. So that's what we're doing here. We're transferring 3 sets of data for our tiles. We can just run them consecutively because after the last execution, X and D will be correct for the next run. So we're doing that there, and we're doing it twice here for our draw tile routine, and that's transferring our program and our bitmaps into memory. The final thing we're doing here is we're running this Yamatile function, and we're going to call that, and the Yamatile function will actually put our command into action. Now we've now got, thanks to our previous execution, we've now got our draw tile routine at CF00 in VRAM, and we're now going to run that, and that's what this is doing here. You can see this time the Yamauchi command is using Chibiko, which is the name of the vampire character that's the mascot for my website. So again, it doesn't need to be Yamauchi there. And what we're doing here is we are starting in the top left of the screen, setting X there. We're specifying our source tile here, and we're going to consecutively fill tiles moving along each time. That's the equivalent of an inc_x. That's a rather odd thing. Load effective address 1,x effectively adds 1 to X because there's no inc_x command on the 6809. But that does do it, and that's moving us down one line after we've done an entire strip. So this is repeatedly calling CF00, and this program is transferred to the sub CPU, and it's run on the sub CPU because we couldn't do it from the main one. So this is effectively employing our draw tile routine to repeatedly draw tiles, and that's what's doing our example for us, and that's what we're doing. So there we go. Okay, well, let's just have a look at that again, but this time we'll change the tile number we're using as a test. We'll use number 2 this time. And there it is. That's rather ugly in that color. Let's change and use all 8 colors and see what it should look like. There we go. That's our crystal from from YQuest there. So that looks a lot better in blue there. So if I just disable use 8 color tiles here, and this time we're going to store our sprite data instead of at C000 to 8000 here. Now that's part of VRAM, and because we've got all 3-bit planes visible, you can see there's some corruption at the top here. Now what we're going to do this time is we're going to hide the 3rd-bit plane so that we can use it for our sprites, because that's what this corruption is. And then we're going to change our palette, and that's going to mean we can have some nicer colors, because even if we've got just 2-bit planes enabled and they're called things like blue and red, we can actually remap them to different colors, and we can do that by disable bit plane 3. You just enable this option here, and you can see they're now blue again, and we're still only using 2-bit planes and the corruption's gone. How have we done that? Well, this is using the masks and the palettes. Here they are. So we've disabled the green bit plane, which is bit plane 3. As I say, these green, red and blue bit planes are actually, they don't have to be green, red and blue. Those are just the default colors. And then we've mapped the colors for our 4 usable colors here to colors that we like. We've got white here, we've got cyan here, we've got blue here, and we've got black here. So this is the 4 colors, and that's why we're able to get those crystals looking good, even though we've disabled one of the bit planes. Now, of course, the only problem with this is if we go back to tile number 3, which was red before, well, of course, that's going to be blue as well now, because we've only got 4 colours, so that's just an unavoidable result of that. But there we go. So here we've got a nice little example of how we can transfer a generic sprite routine that we can use on demand here, and we can then call that into action with this example here. Now, of course, in a real game, you would probably want to convert this and make it take an X and Y coordinate and draw a sprite, or maybe a set of sprites from some kind of list. But again, as I say, this is just an example. The idea was being that this would be your reusable code, and then this would be an example for you to modify as required for your actual sprite drawing needs case by case. So there we go. This, as I say, is an alternate version I was trying to test for speed, and if you're up for a challenge and you're a bit of a 6809 fan, I'd suggest you maybe download this code and try and find a way of making it faster, because I'm sure there is one, and please tell me what you did, because as I say, if I had time, I'd love to really try and grind it down and work out what the fastest way of doing it is, but unfortunately I'm very limited for time these days, so this was the best I could do. And while I don't think it's the best, I was quite satisfied, and it did give me some satisfaction to see what the FM7 is actually capable of, because I didn't really feel that it doesn't really feel like it really got a very good deal. The games I've seen don't tend to be very fast and good and graphical on it, which is a shame. Anyway, there we go. That's all we're going to be covering today. If you liked it, of course, go to my website. You can download the development tools, you can download the example source code for today and the matching sprite files and things, so hopefully you can try it yourself. Anyway, I hope you've enjoyed this. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.